the core problem. Uber is a real-time ride-hailing platform. At its heart, it needs to do three things: let riders request rides, help drivers find those rides, and handle everything in between: pricing, routing, payment, and notifications. The challenge isn't building a basic app. The challenge is doing all of this at massive scale, millions of concurrent users across hundreds of cities with location data updating every few seconds. Before we design anything, let's define our requirements clearly. Functional requirements: what the system must do. Riders can request a ride from their current location. Drivers can broadcast their real-time location. The system matches a rider with the nearest available driver. The system calculates a fare and sends it to the rider before confirmation. Both rider and driver receive live trip updates. Payments are processed at trip end. Non-functional requirements: how the system must behave. Low latency: matching must happen in under 2 seconds. High availability: downtime means lost revenue. Consistency is less critical than availability. It's acceptable if two drivers briefly see the same rider request. The location service must handle millions of GPS updates per second. These constraints will drive every design decision we make. Here's the big picture. At a high level, Uber is built around 5 major components: the client apps for riders and drivers, an API gateway as the single entry point, a set of back-end microservices, a location service that processes real-time GPS data, and a data layer made up of multiple databases and a message queue. All communication flows through the API gateway. The gateway handles authentication, rate limiting, and routes requests to the correct service. The back-end is broken into specialized microservices: trip service, matching service, pricing service, notification service, and payment service. Each service owns its own data store. We'll go deep on each of these now. Let's start with one of the most fundamental pieces of the system: driver location. Every active driver app sends a GPS update every 4 seconds. At peak, Uber has hundreds of thousands of active drivers. That's potentially millions of location updates per minute flooding the system. You cannot write all of these directly to a traditional relational database. The write throughput would be too high. Instead, driver location updates are sent over a persistent WebSocket connection to a location service. The location service writes locations to an in-memory geospatial data store. Redis is a great fit here, because Redis supports geospatial indexing natively with its GEO commands. Redis can store each driver's location as a latitude and longitude pair, and you can query for all drivers within a radius, say 2 kilometers, in milliseconds. Now let's follow what happens when a rider taps Request Uber. The rider app sends a request to the API gateway with their pickup location and destination. The gateway authenticates the rider and forwards the request to the trip service. The trip service creates a new trip record with status Searching and publishes a ride-requested event to a message queue. Kafka is a good choice here. The matching service is subscribed to this topic. When it receives the event, it queries the location service. Give me all available drivers within 2 kilometers of this pickup location. Redis returns a ranked list of drivers by proximity. The matching service picks the closest available driver and sends them a ride request. The matching service is the heart of the system, so let's go deeper. A few design considerations. First, driver availability. The matching service needs to track which drivers are available. You can maintain a simple in-memory set of available driver IDs or store availability as a flag alongside their location in Redis. Second, what if the first driver declines? The service falls back to the next closest driver and repeats the process. This fallback loop runs until a driver accepts or a timeout occurs, at which point the rider is notified that no driver is available. Third, concurrency. 2 riders in the same area could trigger matching at the same time. To avoid assigning the same driver to 2 riders, you can use an optimistic lock. Mark the driver as tentatively assigned in Redis with a short TTL before confirming. Once a driver accepts, the trip service updates the trip status to driver en route and notifies both parties. A trip has several status transitions, and the trip service owns all of them. Here's the life cycle: searching, then driver assigned, then driver en route, then rider picked up, then trip in progress, then trip completed, and finally, payment processed. Each transition triggers side effects. For example, when a driver is assigned, the notification service sends a push notification to the rider. When the rider is picked up, the trip service begins tracking distance for fare calculation. When the trip ends, the payment service is triggered. All of these events flow through Kafka. The trip service publishes state changes. Downstream services, notification, payment, analytics, consume those events independently. This decouples services and keeps the system resilient. Uber's pricing model is simple in concept but complex in implementation. Base fare is calculated from three things: a flat pickup fee, a per-minute rate, and a per-kilometer rate. This is straightforward. Surge pricing is more interesting. When demand in an area significantly exceeds supply, Uber applies a surge multiplier. The pricing service monitors the ratio of active ride requests to available drivers, aggregated by geographic zone. Uber calls these hexagonal zones, computed with a library called H3. When demand to supply in a zone exceeds a threshold, the multiplier kicks in. The multiplier is shown to the rider before they confirm, and it gradually decreases as more drivers move into the area. This pricing data is computed in near real time using a stream processing pipeline. Apache Flink or Spark streaming work well here. The notification service handles all real-time alerts to riders and drivers. It consumes events from Kafka: driver assigned, driver arrived, trip started, trip ended, payment processed, and translates each into a push notification. For mobile push, it uses Apple's push notification service for iOS and Firebase cloud messaging for Android. For SMS fallback, it integrates with a provider like Twilio. The key design here is that the notification service is purely event-driven. It does not make synchronous calls to other services. It just listens and fires. This keeps it lightweight and easy to scale independently. Let's talk about the databases. Different services have different data needs, and using a single database for everything would be a mistake. User profiles and trip history are stored in a relational database like PostgreSQL. This data is structured, requires strong consistency, and benefits from ACID transactions. Driver locations are stored in Redis with geospatial indexing, as we discussed. Redis keeps this data hot and queryable in sub-millisecond time. Trips in progress are also cached in Redis for fast reads during the active trip. Driver earnings, trip analytics, and reporting are written to a data warehouse like Amazon Redshift or BigQuery via a batch pipeline. These queries are analytical and can tolerate latency. Messaging between services is handled by Kafka, which also serves as a durable event log for replaying events in case a consumer is down. Now let's talk about the hard parts, where most systems break at Uber's scale. Location service write throughput. Millions of GPS updates per second. The solution is horizontal scaling of the location service with Redis cluster, sharded by geographic region. Matching under load. During peak times, Friday nights, New Year's Eve, matching requests spike. The matching service is stateless, so it scales horizontally easily. The bottleneck is Redis, which you handle with red replicas. Database hotspots. Popular areas generate more trips, creating uneven load on the trip database. You shard the trip table by geographic region or use consistent hashing by trip ID. The thundering herd problem. When surge pricing ends in an area, all queued riders send new requests simultaneously. You handle this with jitter, randomizing retry delays to spread load over time. Single points of failure. Every service must have multiple replicas. Kafka must run as a replicated cluster. Redis must be configured with replicas and Sentinel for failover. What happens when things go wrong? If the matching service crashes mid-match, the trip event remains in Kafka. When the service recovers, it reprocesses the event. Kafka's consumer groups ensure exactly once or at least once processing, depending on how you configure offsets. If a driver's app loses connectivity, their last known location stays in Redis with a time to live. If no update arrives within 30 seconds, they are marked unavailable. If the payment service fails at trip end, the payment event stays in Kafka and is retried with exponential backoff. Payment is processed eventually. The rider is never double-charged because the trip ID is used as an idempotency key. Circuit breakers prevent cascade failures. If the pricing service is slow, the system falls back to a cached base fare rather than blocking the entire ride request. Let's recap what we built. We designed a system that handles millions of concurrent users with a location service backed by Redis for sub-millisecond geospatial queries, a matching service that uses proximity search and optimistic locking to avoid double assignment, a trip service that manages state transitions and coordinates downstream services, a pricing service that applies surge multipliers based on real-time demand and supply data, a notification service that is purely event-driven and decoupled from the rest of the system, Kafka as the messaging backbone for async communication between services, and a data storage strategy that matches each service's read and write patterns. For your interview, start with requirements, always. Clarify both functional and non-functional before drawing anything. Then sketch the high-level architecture before going deep. Justify every major choice. Why Kafka? Why Redis? Why PostgreSQL? The interviewer wants to see that you can reason about trade-offs, not just recite patterns. If you want to practice more system design, the next videos in this series cover WhatsApp, Twitter, and Netflix. Drop a comment if you want a deeper dive into any component, the matching algorithm, the H3 geospatial indexing, or the payment retry logic. Subscribe if this was useful. See you in the next one.